Hi, so welcome to this video on power series. What we will be doing here is basically a precursor to generating functions. So the next video onwards, we'll be starting our understanding, starting to understand what generating functions are. So before that, we have to cover this because this is required for that. So what is a power series? A power series is an infinite series of powers in some variable. So let's look at the formal definition of that. So a power series about x is equal to 0 is a series that looks like this. Summation from n is equal to 0 to infinity cn x power n. Now, if you write that out, you will get c0 x power 0, which is 1, plus c1x plus c2x square, and so on, cn xn plus. This goes on till infinity, right? Now, here x is equal to 0 is called the center of the power series. Center of the power series. That is just a term, so you don't need to worry about that. In case you want to change the center, you can create a power series about x is equal to a. So about x is equal to a, the power series is a series that looks like this. Summation n 0 to infinity again, cn x minus a power n. So now you're getting c0 into 1 plus c1 into x minus a, c2 x minus a whole square, and so on. So nth term will be cn x minus a whole power n. Keep in mind that here, all of these C0, C1, C2, all of these are constants, right? The constants could be real numbers, could be complex numbers. So right now, we don't worry about complex numbers so much. What we'll do is work in real numbers with this definition of a power series, which is basically an infinite series of powers, right? And there are some constants attached. What we learn is these operations on power series. So power series can be manipulated. Like even though there are infinity terms, you can still define addition, subtraction, multiplication. You can even do differentiation and integration for the power series. Now, addition and subtraction are fairly obvious. What you do is if you add two power series, you will add the coefficients with the same powers, right? So suppose I have to add this one and this one, I will say the resulting power series will have coefficients C0 plus C0, so 2C0 plus C1 common x plus x minus a, right? Actually, you will collect all the powers together. So C0, this will have a C1 minus a term, so that will go in the constant term. So we will look at addition and subtraction soon, and then multiplication, differentiation, and integration. But before that, what we want to do is look at a basic power series that you are all familiar with. So you know the sum of this series, right? When you have studied GPs or geometric progression, you know that this series will be equal to 1 by 1 minus x if mod x is less than 1, right? If the common ratio of the GP is less than 1, right? So this series can be written now as n is equal to 0 to infinity x power n is equal to 1 by 1 minus x. Here what happens is each of the Ci, each of the C's, right, are equal to 1, correct? So this is a power series. And what we can think of is this particular function is being approximated by the power series, or is being approximated by this sequence of polynomials, right? So 1 by 1 minus x can be written as 1 plus x square, and so on. And if your x is close to 1, is close to 0, then x square, x3, and so on are tending to 0. So you can sort of ignore them. You can sort of ignore them in comparison to x. X is bigger than them. X is much bigger than these terms because x is very close to 0. So you can sort of write 1 by 1 minus x is approximately equal to 1 plus x, right? So that is a useful application of power series where we are able to approximate some weird looking function in a different way, which is a simple polynomial, right? Every power series expansion is basically a polynomial, but it has infinite terms. Now, if for a particular problem you need to apply only till second degree, then you can just take 1 plus x square as your approximating polynomial, right? This is an approximation, but in many physical problems, you will realize that power series approximations are very useful. So Next thing that we want to look at is a theorem which helps us basically differentiate and integrate power series. So let's look at it. If summation of Cn x minus a power n, this is obviously n goes from 0 to infinity. If this series converges, and we discussed convergence and divergence of infinite series in the last video. If it converges, basically means the sum tends to go close to a particular limit, right? So if it converges for x belonging to a minus r to x to a plus r, right? So this is called the interval of convergence of the power series. So to simplify matters, think about when does this series converge? The GP series that we have been looking at, when does this series converge? You have to say x is less than 1, right? Then only it will converge, when common ratio is less than 1. So you can write this as -1 is less than x is less than 1, right? So the interval of convergence for the GP power series is -1 to 1. So similarly, if this power series converges for x ranging from a minus r to a plus r, where r is a constant, that constant is sometimes termed radius of convergence. Where r is a constant, which is called radius of convergence, if the series converges, then we can define f of x to be equal to a function f of x, which will be a polynomial, which will be equal to summation of n is equal to 0 Cn x minus a to the power n from a minus r. Only in the interval of convergence can you define this function. Only in this region can you define this function, because only in this region will this series have a particular limit and it is converging, right? If the series is diverging, if you go outside this interval, the series diverges. So function is not properly defined because it will tend to infinity then, right? So you want a function which is finite and all. So this is a properly defined power series which converges to fx, right? This function, the theorem says that this function will be differentiable inside this interval, inside this interval. And basically now you can differentiate it as you regularly do differentiation, and you can create a new series. F dash x will be what? F dash x will be n is equal to 0 infinity. Now n will come down, n Cn and x minus a to the power n minus 1. This is your new series, right? After differentiating. So I'm writing it in the summation notation, but actually you can think of it as just when you put n is equal to 0, right? You get C0, and C0 is a constant. So C0 will disappear actually here. The basic power series was C0 plus C1 x minus a. So think about it. The basic power series was C0 plus C1 x minus a plus C2 x minus a whole square. So upon differentiation, you will get C1 plus 2C2 x minus a plus 3C3 x minus a whole square, and so on. So this is the differentiated function, and this is also a power series, and this power series will also converge inside this interval, inside the interval a minus r is less than x is less than a plus r. Now obviously this is a theorem that is saying that if one power series converges, then if you differentiate it, the next power series will also converge in that same interval, right? F dash x will also converge. So this theorem has not been proved right now. We have not proved it, but obviously we'll omit the proof for now, because the proof is probably a little too advanced for this video. So we'll not do the proof. We'll just assume that it is correct, and f dash x is another new power series which can be defined like this. So what is the use of this theorem? This theorem basically helps us differentiate different power series. And how can we use that? So for example, if someone asks you the power series for 1 by 1 minus x whole square, or basically they may not ask you in that way. They may ask you, what is this function? What is the coefficient? What is the coefficient of x square in the expansion of 1 by 1 minus x squared. This could be a question. This type of question happens a lot in combinatorics, right? So if this is a question, then what I will do, I know the power series for 1 by 1 minus x is equal to this, right? Now from the theorem, it is assured that whenever this converges, which happens when this is true, in that interval, you can differentiate it and get a new power series. Differentiating it, I will get minus 1 by 1 minus x whole square multiplied by minus 1 is equal to 1 plus 2x plus this term was x cubed, so it will be 3x square and so on, right? So now I have gotten a new series for 1 by 1 minus x square, which is 1 plus 2x plus 3x square plus so on, right? So now I can answer the question, what is the coefficient of x square in the expansion of this? Coefficient of x square is just 3, right? So this type of manipulation is possible because of the previous theorem, right? Now let's see how we can integrate it. So again, it is fairly simple. You can do term by term integration for power series. Term by term integration. So again, I will state the theorem without proof. So suppose fx is equal to summation of n is equal to 0 to infinity cn x minus a power n converges for a minus r is less than x is less than a plus r, then integral of fx dx, right? Integral of fx dx, which is equal to, we integrate each term. So what the series will look like is n is equal to 0 to infinity. Now x minus a power n integration will be x minus a power n plus 1 by n plus 1, and the constant will be there, right? Plus a constant. Constant comes because of the integration. So what is happening here is we have defined a new series, new power series, which is done by doing a term by term integration of the original power series. Term by term integration of the original series. And this, we are assured that this power series also converges in that interval, also converges in that particular interval. A minus r is less than x is less than a plus r, right? So let's see some application of this so that we can understand it better. So suppose there is a question like this: identify the function f of x is equal to x minus x cubed by 3 plus x5 by 5 minus this, and find the value of f of 1, right? Correct. This is a question for us. So basically they can just ask you what is f of 1 if f of x is this series, right? So what we will do is, first we will try to differentiate this. Let's say f dash x. We do f dash x, we know how that power series can be differentiated, and this one will become 1 minus 3x square by 3 plus 5x power 5 by 5 and so on, right? By 4, 5x power 4 by 5 minus so on. This is the series that we are getting. So this series looks like what? 1 minus x square plus x power 4. Next term should be x power 6 and so on. Now clearly we know that this is a GP with common ratio of minus x square, right? So the sum of this GP can be written as 1 by 1 minus x square, which is equal to 1 by 1 plus x square, right? Now we know that I can now integrate this f dash x, right? Because this is df of x by dx is equal to 1 by 1 plus x square. So I can write df of x is equal to dx by 1 plus x square. And this is a fairly simple integral. Like if I integrate dfx, I will get basically integral dx by 1 plus x square. And this integration is obvious to anyone who has done basics of integration. So this is actually tan inverse x plus some constant, right? Now integration of d of fx becomes f of x. F of x is becoming tan inverse x plus c. Now what is the constant value? The constant value can be gotten by checking the value of f of 0. F of 0 in this function is equal to 0. So if you put 0 here, you'll get f of 0 is equal to tan inverse 0, which is 0 plus c. So therefore c must be 0. So this implies c is equal to 0. So I have identified the function as tan inverse x, right? By actually differentiating f dash x and then integrating. So I'm doing two opposite operations, if you realize that. So one time I differentiated and the next step I integrated, right? So actually it becomes f dash x itself, right? But the beauty of it is that differentiation and integration done properly will give you the tan inverse x interpretation of this function, right? Now it is very easy to find f of 1. F of 1 is tan inverse 1, which is pi by 4. So by the way, this is a theorem this is a series that was proved by Leibniz, and Leibniz basically figured out that pi by 4 is equal to 1 minus 1 cube by 3 plus 1 by 5 minus 1 by 7 plus and so on, so on. Because 1 cube is actually 1. So pi by 4 is actually the sum of this series, 1 minus 1 by 3 plus 1 by 5 minus 1 by 7, correct? And he estimated, basically this was Leibniz series, and he estimated the value of pi in this way. Pi is equal to basically 4 times 1 minus 1 by 3 plus 1 by 5 minus 1 by 7 and so on. So you are seeing where suddenly you are getting an estimate for pi, right? So this is a nice application of power series. Here basically we got this power series for tan inverse x as x minus x cubed by 3 plus x power 5 by 5 minus x7 by 7 and so on. And we put 1 in that, right? Correct. So now that we know integration, differentiation, addition and subtraction are obvious, let's discuss multiplication of power series. So we can even multiply two different power series. So if ax is equal to summation of n is equal to 0 to infinity an x power n, and bx is equal to summation of n is equal to 0 to infinity bn x power n, and suppose both of these series converge for mod x is less than r, then what the theorem says that we can create a new series, right? We can create a new series c of x, which is equal to summation of n is equal to 0 to n infinity cn x power n, where each cn is equal to Cn is basically a0 bn plus a1 bn minus 1 plus a2 bn minus 2, so on till an b0. So it can be written in a succinct manner like this: k is equal to 0 to n ak bn minus k. So what is all this? What is this thing? This is fairly simple actually. Ax, you are taking one power series multiplying by another power series, and you are getting a new series which is the product series. And the rule here is typical normal multiplication rule, right? Like suppose you had one series like this, 1 plus x plus, actually I'll just do the example in the next page. So I will show you an example of multiplication and you will realize that it is fairly obvious. So you can note down this or pause the video and try to understand this. This is basically simple coefficient of x power 0 here, and b power n is bn is coefficient of x power n in the other series. So you're just multiplying terms which give rise to the same powers. So let's do an example for this multiplication. So the question is, find the power series of 1 by 1 minus x square. But this time, remember that we got this by differentiating the power series of this, right? If you differentiate, you will get the power series of 1 by 1 minus x square. We have already done that before, but this time we'll get it in a different way. We'll multiply the power series of 1 by 1 minus x into the power series of 1 by 1 minus x. And that way we will get this now. And we should expect that the answers should match, right? So let's define first power series ax as summation of n is equal to 0 infinity an xn is equal to 1 plus x square plus xn, so on, right? So clearly this is 1 by 1 minus x, right? And similarly bx we define as another power series This is 0 to infinity bn xn, and that is also identical to this. Correct? That is also identical. It is also 1 by 1 minus x. So multiplying them, let's write down the term Cn. Cn is basically coefficient of x power n in the resulting power series. So it will be a0 bn plus a1 bn minus 1 and so on till an b0. So now notice that each of the ans is 1. A1 is 1, A2 is 1, everything is 1. So it is 1 and BNs are also 1. So 1 into 1 plus 1 into 1 plus 1 into 1, so on till 1 into 1. How many terms are here? There are n plus 1 terms. So you are getting Cn is equal to n plus 1, right? So the resulting power series will basically be, according to our prediction, it should be summation of n is equal to 0 to infinity. Cn is n plus 1 x power n. So what should I write it? I should write it like this. It will be 1 plus 2x plus 3x squared plus 4x cubed and so on. This is my resulting power series expansion for 1 minus x squared. So the same answer comes on differentiation. Differentiate this series and see, it will be 1, 2x, 3x squared, n, x, n minus 1 and so on, right? So that is the same series that is coming. So basically we have learned how to multiply. For multiplication, you just have to find out the Cn term. Cn term will be this thing. Take the initial power series, multiply x power 0 coefficient with x power n coefficient here, and then x power 1 coefficient with x power n minus 1 coefficient here, so that you can always match the correct powers. So I hope that is clear. Now what we look at is two special power series. Two special series, which are basically called the Taylor and Maclaurin series. Taylor and Maclaurin series. Now, these are very important and these are applicable in many different areas in physics and maths. So what we'll write is basically we'll define the Taylor series, right? So I will derive actually what this means. So far what we have been seeing is that the sum of a power series is a continuous function, and is differentiable in the interval of convergence. So now what we'll look at is we'll look at the opposite problem as in, so we say if a function is differentiable in some interval, can we write it as a power series? Can we approximate it as a power series? That is the question that we are trying to answer. So the answer to that question is yes. The proof of that we can write it as a power series is slightly advanced. We'll not cover the proof of it. What we'll do is how we will get the power series. So the answer to the question, can we write a differentiable function in some interval as a power series, is yes. Yes, we can. But the question is, what are the coefficients? What are the coefficients of that power series, right? Of that power series. Correct? So what we are saying is fx, if it is differentiable in some interval, can be written as summation of n is equal to 0 to infinity, let's say an x minus a to the power n. Our question is, what are the an? What is an, right? Now that can be gotten quite nicely. I will just show you the derivation quickly. So if f of x is equal to summation of n is equal to 0 to infinity an x minus a power n, we will have the series looks like this: a0 plus a1 x minus a plus a2 x minus a whole square and so on. So if I differentiate this, f dash x will become what? F dash x will look like a0, no, not a0, a1 plus 2a2 x minus a plus so on, right? And f double dash x will become a 2a2 plus 3a3 x minus a plus it will be 3 into 4 x minus a4 x minus a whole square and so on. And f triple dash x, you can check it by expanding each term and differentiating properly. I'm not writing all the terms here, but you can check and confirm that this is correct. This will be 3a3 plus 3 into 4 into 2. So 2 into 3 into 4, a4 x minus a plus 3 into 4 into 5 x a5 x minus a whole square and so on, right? I'm just differentiating and checking, writing all the terms properly. So similarly, if I keep doing it, if I differentiate n times, this is denoted by the symbol where n is on top in a bracket. F of n times differentiated would become what? It would become, following the same pattern, it should become n factorial an, right? N factorial an plus here I have made a mistake. It is 1 into 2 into 3a3 and this is 1 into 2a2. Why is that true? Because the previous series, the double derivative series was 1 into 2 into a2 plus 3 into a3 plus 2 into 3 into a3, right? Because this term was 3a3 x minus a whole square. So this differentiation will become 2 into 3 into a3, right? See, I made a mistake there when writing. So you can see that this is 2 into 3 into a3. So after differentiation, this term becomes 0. So it becomes 1 into 2 into a3, which is basically 3 factorial into a3, right? This term. And this first term was 2 factorial into a2. So therefore, you can see that the pattern is n factorial into an when you do nth derivative plus some terms containing x minus a, right? So this differentiation series we have calculated. Now because a lies in the interval of convergence, we can put the value of a in this. Basically, a is a point which is inside that interval in which the power series converges. So we can put the value of a in all of these steps and we get f of f dash a. F dash a is what? If you put a, all of these other terms vanish. F dash a is simply a1. F double dash a is what? F double dash is simply 2a2, right? Or basically 2 factorial into a2, right? F triple dash a is what? F triple dash a is, see, 3 factorial into a3, 3 factorial into a3. And similarly, f nth derivative at a is going to be equal to n factorial into an, right? So this now beautifully gives us the coefficients, right? So this gives us a1 is f dash a2 is f double dash a by 2 factorial, a3 is f triple dash a by 3 factorial, and an is basically f nth derivative at a by n factorial. So what we are getting is an is coming as f nth derivative at a divided by n factorial. So that gives us immediately the Taylor series expansion, which is f of x will be, generally you're supposed to write how? You're writing a0 plus a1 x minus a plus a2 x minus a whole square plus so on. So now what you will write, because you know the values of the coefficient, a0 is 1. A0 is actually, what is a0 here? A0 is f of a, right? When you put x is equal to a in the original equation. So f of a plus a1 becomes f dash a into x minus a, f dash a by 1 factorial actually. And this is f double dash a by 2 factorial, x minus a whole square. And similarly, nth term is f nth derivative at a by n factorial, x minus a power n plus so on. So this is my expansion. This expansion is called Taylor series expansion of a function at a certain point x is equal to a, right? So Taylor series expansion at x is equal to a. At x is equal to a. If you put x is equal to 0 here, right? Or basically you are saying that about a is equal to 0. You are doing the Taylor series about a point a is equal to 0. Then you get a new series which is called the Maclaurin series, which is given by f of 0 plus f dash 0 by 1 factorial x plus f double dash 0 by 2 factorial x square and so on. So this series is called the Maclaurin series. Maclaurin series expansion. Now, what is the purpose of these expansions? These expansions help us do many things. So what we can say is these Taylor series and Maclaurin series are valid for all infinitely differentiable functions. Infinitely differentiable functions. So you can basically find the expansions for e power x, sin x, cos x, tan x, tan x in a particular range, however, from minus pi by 2 to pi by 2, because at that point at pi by 2 it goes up to infinity, so there it is not converging. So you can restrict yourself to certain domains for certain specific functions, but for these functions there is no problem. Even tan inverse x when x is between -1 to 1, right, and so on. So different Taylor series expansions you can create. And for example, e power x evaluated at, let's do the Maclaurin series for e power x. That will be f of 0 plus f dash 0 by 1 factorial x power 1 plus f double dash 0 by 2 factorial x square and so on. So f of 0 is 1 plus f dash x is always e power x. So you'll get e power 0. So that is equal to 1 into x by 1 factorial plus x square by 2 factorial. Every time derivative of e power x is same as e power x, and when you put 0 it becomes 1. So each coefficient is 1 in this expansion. So this is going to be your expansion for e power x. So similarly, you can derive expansions for sin x, cos x, e power x. Why is this useful? Because these are useful in limit calculations. First of all, in your limits chapter, you will need to know Taylor series and Maclaurin series expansion for some indeterminate forms. So you'll have sometimes forms which are 1 power infinity and so, or infinity by infinity. In these forms, when the limits come, you can use them to evaluate the limits. One more application that you might not be aware of, I will show you just now. So these Taylor series expansions are very useful in solving differential equations. Solving differential equations. So generally, differential equation solutions is a huge topic and many different methods are there. But power series solutions are one of the prominent methods that help us solve many different classes of integrals that are otherwise not solvable. So for example, we will take an easy example right now. Let's say dy by dx minus y is equal to x. This integral can be solved by regular methods that you learn in 11th and 12th. But what we are doing here is trying to get it through a power series method, right? So how do we do that using power series? So what we are going to say is let, and what more is given here, y0 is equal to 1. So this is the information provided to us, that dy by dx minus y is equal to x, and y at 0 is equal to 1. So we have to find y is equal to fx. What is it, right? So let's assume that y is a power series, right? Let's say y is equal to fx is equal to a0 plus a1x plus a2x square. This is the Maclaurin series for y. This is a solution to the differential equation, solution to the DE. So why are we able to assume this? Because whatever be the function f of x, it is possible to express that as a power series expansion. So even though it might not be 100% accurate, it is a very good approximation. Any function in a differentiable interval can be expressed as a power series. So we are just saying that let y is equal to fx, which is the solution for this differential equation, be written as this power series. So then what we can do is y dash is clearly going to be a1 plus 2a2x plus 3a3x square and so on, right, for us. So we have to put that in this y dash minus y is equal to x. So therefore, y dash minus y looks like a1 minus a0 plus 2a2 minus a1, 2a2 minus a1x plus 3a3 minus a2x square and so on, right, is equal to x we are getting. I'm just putting y dash and y and subtracting and writing it equal to x according to the original equation. So that immediately gives us a1 minus a0 is equal to 0 because this polynomial has to be equal to this infinite polynomial. And 2a2 minus a1 is equal to 1 and everything else will disappear. 3a3 minus a2 is 0 and so on. And finally, you'll get one equation nan minus an minus 1 is equal to 0. So what is the meaning of these values? How can you find the a0, a1, a2 and all from here? So first we can also use this thing, which is given, which is saying that f of 0 is equal to 1. So if you put f of 0 in this, you get a0, right? So this tells us that a0 is equal to 1 because f of 0 is 1 and f of 0 here will be just a0. So since a0 is 1, we get a1 is equal to a0 is equal to 1, right? And a1, a2 is equal to a1 by 2. So a2 is half. a3 is equal to a2 by 3. So a2 is half. So 1 by 2 into 3, right? Correct. Which can be written as 1 second. We have a2 is equal to a1 by 2, which is equal to a1 is, no, I have made a mistake. My equation is only wrong here. So a2 is not equal to a1 by 2, obviously. a2 is equal to 1 plus a1 by 2, right? a2 is equal to 1 plus a1 by 2, which is giving answer of 2 by 2, right? And a3 is equal to a2 by 3. So it is going to be 2 by 2 into 3, right? And similarly, a4 will be equal to, a4 will be similarly equal to a3 by 4, right? So that will be 2 by 2 into 3 into 4, right? So you are noticing a pattern. a2 is becoming 2 by 2 factorial, a3 is becoming 2 by 3 factorial, a4 is becoming 2 by 4 factorial. So what we get is all the coefficients we have gotten. a0 is 1, a1 is 1, and after that a2 is 2 by 2 factorial, a3 is 2 by 3 factorial, a4 is 2 by 4 factorial. So my series solution for this differential equation given y0 is equal to 1 is coming as f of x is equal to a0, let's write it first once, a0 plus a1x plus a2x square plus a3x cube and so on, plus an x power n. And what we get is a0 is 1, a1 is 1, a2 is 2 by 2 factorial x square. This is 2 by 3 factorial x cube and so on. Same pattern repeats. This will be 2 by n factorial x power n plus so on. So how is that helpful? Because that now we can take 2 common here and write it as x square by 2 factorial plus x cube by 3 factorial and so on. This is the series. Now notice that this is just e power x minus 1 minus x. Earlier we saw the power series expansion for e power x. E power x was equal to 1 plus x square by 2 factorial plus x cube by 3 factorial and so on. So this is just that. So 2 times this plus 1 plus x. So my fx is becoming 2 e power x minus 1. That is my solution of this differential equation. You can now check it, it will work. You can check the derivative of this fx and subtract fx from it and you will get x as the answer. So let's do that. F dash x is what? 2 e power x minus 1. So if you subtract f dash x 2 e power x minus 1 minus 2 e power x minus 1, notice that you are just getting x, right? So this function that we have obtained is the correct answer for this differential equation. So this was a fairly easy example. However, when you do a little more advanced physics and all, you will need to solve a lot more difficult differential equations which you can solve by power series methods. So I hope this video helps you understand power series and basically be able to manipulate power series. So addition, subtraction, differentiation, integration, and all of these operations you should be able to easily do, multiplication as well, right? This will be important as we go forward, because when we do generating functions, we will require all of this knowledge, because we have to manipulate generating functions, find the coefficients of certain powers in certain series, right? So you will see how this is relevant in the next few videos in the combinatorics lecture. See you next time.